Okay, so for today, we're starting a new chapter. Always exciting. This is the Laplace transform. Now, the book has chapter 6 as the Laplace transform, and then it has section 6.1 titled the Laplace transform, which to me is an indicator of bad title design, but whatever, we'll go with that. 6.1, the Laplace transform. So, first of all, in today's lecture, we're not going to talk very much about ODEs. The reason why is because we need to build up how to do these Laplace transforms before we can actually apply them to solving ODEs. So for today, we're just going to talk about what this thing is and how to compute it. Okay? Eventually, this is going to lead us to a method of solving linear ODEs with constant coefficients, even if the inhomogeneous term might not be differentiable or even continuous. But for now, we're just going to focus on what this thing is and how to compute it. So, definition. Let f be a function of a single variable which we might as well call t, defined for t greater than or equal to 0. The Laplace transform of f is the function of the single variable s. So the emphasis here is that s is not t. That the Laplace transform is a function of a different variable than the original. Okay. So it's the function of the single variable s defined via f of s. So in this chapter, we're going to let lowercase letters indicate the original function of t, and let uppercase letters of the same letter indicate the Laplace transform, which is a function of s, as I said. This is the integral, the improper integral, from 0 to infinity of e to the negative st times f of t integrated with respect to t. Where this improper integral converges, that is. Yeah, let me write that. Where the improper integral converges. Defined where the improper integral converges is what I'm trying to say. Okay, so an alternate notation, which we will also use, is script L of f of t. Now, this notation comes with a disadvantage, which is why it's not the only notation we're going to use. This comes with the disadvantage of not explicitly stating that this thing is a function of s, which is different from t. Okay? Right, so of course, we're going to do some examples to get used to computing this thing. So, example. Find the Laplace transform of the function f of t equals 1. We'll start with a simple example. Okay, so let's think about that for a second. If the function is f of t equals 1, then the Laplace transform of f of t, which we're going to call capital F of s, as I said, this is going to be equal to the integral from 0 to infinity of e to the negative st times 1 dt. Okay? Now, if you remember from Calculus 2, every improper integral is in fact a limit. So this is the limit as b approaches positive infinity of the integral from 0 to b of e to the negative st dt. Okay? So now, again, cannot stress enough, s and t are not the same thing. Therefore, s is a constant with respect to t. Okay? So we're going to regard this as if it were e raised to a constant times t. Now, if you have e raised to a constant times t, the antiderivative there, the antiderivative is going to be 1 over that constant times e to the negative times e to the constant times t. And then this is evaluated from 0 up to b. Okay? Oh, let me be clear here. This is evaluated from t equals 0 to t equals b. Because, again, s is a constant with respect to the variable that we're integrating out. Okay? So, this is the limit as b approaches infinity of, let's see here, negative 1 over s e to the negative bs minus negative 1 over s e to the negative 0s Okay. Then as b approaches infinity, this term approaches 0 because we have e raised to a negative exponential, or a negative exponent. So as b approaches infinity, e to the negative bs approaches 0. And then this term just stays here. So we have negative 1 over s times e to the 0, which is just 1 over s. So f of s equals 1 over s. That is our Laplace transform. Okay? Let's do some more examples. So find the Laplace transform. Of the function f of t equals t. Again, starting with some pretty simple functions of t, just to get us started. Right, so once again, the Laplace transform, by definition, this is the integral from 0 to infinity of e to the negative st times t dt. Okay. So, again, by definition, the improper integral is a limit. The limit as b approaches infinity of the integral from 0 to b of t e to the negative st. So then we need to find the antiderivative of t e to the negative st. Well, if you remember, that is a quintessential integration by parts problem. You have t times an exponential, right? So what we'll do is integration by parts here with u equals t and dv equals e to the negative st dt. In that case, du is dt, and v is negative 1 over s e to the negative st. Right? So, this is going to be the limit as b approaches infinity of, let's see here, uv is going to be negative 1 over s times t times e to the negative st, and that's evaluated from 0 to b, minus the integral from 0 to b of v du, which is going to be negative 1 over s e to the negative st dt. Okay, so then 1 over s is a constant, which means we can pull it outside the integral. So this becomes the limit as b approaches infinity of negative 1 over s t e to the negative st, evaluated from 0 to b, plus 1 over s integral from 0 to b e to the negative st dt. Okay. So the antiderivative of e to the negative st, once again, is negative 1 over s e to the negative st. So this becomes the limit as b approaches infinity of negative 1 over s t e to the negative st minus 1 over s squared e to the negative st, and all of this is evaluated from 0 up to b. Okay. Now, in order to take this limit, we're going to have to use L'Hopital's rule because we have t, which is a linear polynomial, times a negative exponential. So, well, let me rewrite this and then we'll be able to make more sense of it. This is the limit as b approaches infinity. Actually, first of all, we need to evaluate at 0 and b, so let me do that first. So we have negative 1 over s, b, e to the negative bs, minus 1 over s squared, e to the negative bs, minus, okay, when t equals 0, this first term is just 0. And then this last term is just negative 1 over s squared. And b is approaching infinity. Okay, so this term right here is going to approach 0. You know it's going to approach 0 because it's e raised to a negative exponent. B is approaching infinity. This one right here, though, in order to figure out what it's approaching, because b is approaching infinity, but e to the negative bs is approaching 0, so that gives us an indeterminate form of type 0 times infinity, if you remember from L'Hopital's rule from Calculus 2. So to handle this, we're going to rewrite it. First of all, we can ignore this term now because we know it's going to approach 0. So let's just focus on this term. We have the limit as b approaches infinity of negative, 1 over s b over e to the bs. And then we still have this plus 1 over s squared. Of course, the limit as b approaches infinity of 1 over s squared is just 1 over s squared because b doesn't even appear in that. So we have limit as b approaches infinity, b over e to the bs. That's a type infinity over infinity fraction. So we can apply L'Hopital's rule. So if you take the derivative with respect to b, this becomes the limit as b approaches infinity of negative 1 over s, 1 over s e to the bs. And then we still have plus 1 over s squared. Well, as b approaches infinity, e to the bs approaches infinity, and therefore 1 over that approaches 0. So altogether, what we get here is 1 over s squared, and that is our Laplace transform of t. Okay. Now, let's do one more example. For this one, I'm going to define what we're going to call the unit step function, or Heaviside function. So, definition. The unit step function or Heaviside function is the piecewise function defined via u of t. So for the remainder of this chapter, u is going to refer to the unit step function. If you can't already tell, this function is going to be very important to us. So u of t is just going to be 1 for t greater than or equal to 0, and 0 for t less than 0. So if you were to draw a graph of this function, it's a very simple piecewise function. We have t and y here. U of t just looks like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, up until t equals 0. And then it's just 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay? So let's try to find the Laplace transform of a function involving the unit step function. So example, find the Laplace transform of f of t equals u of t minus a, where a is a constant. Okay. So once again, directly from the definition of the Laplace transform, this is going to be the improper integral from 0 to infinity of e to the negative st times u of t minus a dt. By definition, that means the limit as b approaches infinity of the integral from 0 to b of e to the negative st times u of t minus a dt. Now at this point, you might be a little perplexed as to how to go forward, because you're thinking to yourself, like, isn't this a piecewise function? How do you integrate a piecewise function? Well, it's actually quite easy. You integrate a piecewise function by just splitting it up into its pieces, and then taking the integral of those pieces. So first of all, let's understand that u of t minus a. So if you take u of t and you replace it with u of t minus a, what you're going to get is 1 for t greater than or equal to a, and 0 for t less than a. So it shifts this center, so to speak, of the Heaviside function. So let's say a is right here. What we get here is just 0 throughout until we get up to a, at which point we jump up to 1. And so we're looking at a function that looks sort of like that. So, what we need to understand here is that this is just 0 for when t is less than a. So, when t is less than a, all right, that's in this diagram, we're integrating from, so we're integrating from 0 to b. So in this diagram, that means that from 0 up to a, the integrand is 0, which means we can ignore that portion. Okay? So what I'm saying is like this. This is the limit as b approaches infinity of the integral from 0 to a of e to the negative st u of t minus a plus the integral from a to b e to the negative st u of t minus a We can agree on that, right? We can agree on that because when you have a definite integral from 0 to b, you can split that into a definite integral from 0 to a plus a definite integral from a to b. Okay. So, let's say that a is greater than 0, which is what we're proposing in this diagram here. Yeah, let's actually put that condition in. A is a constant, a is greater than 0. Just to simplify things. The truth is it won't actually make a difference whether a is greater than 0 or not, but that's fine. So if a is greater than 0, then we're integrating from 0 up to a of 0. U of t minus a is 0 in that location, so we can just replace this u of t minus a with a big 0. And then over there, u of t minus a from a up to b, b presumably is greater than a, because b is approaching infinity. This is just going to be 1. So altogether, this thing, the integral of 0 is just 0. And what we end up with here is the limit as b approaches infinity of the integral from a to b of e to the negative st. So you do that antiderivative. You get the limit as b approaches infinity, negative 1 over s, e to the negative st, evaluated from a up to b. To evaluate this, you get the limit as b approaches infinity, negative 1 over s, e to the negative bs minus e to the negative as. So as b approaches infinity, this thing just approaches 0. And what we end up with here is 1 over s, e to the negative as. And that is our Laplace transform of u of t minus a. Okay? So I had to go through this. I had to go through this process of computing the Laplace transform directly from its definition in the same way that when you first learned how to do a derivative, you needed to learn how to do that directly from its definition, which was the limit as h approaches 0 of f of x plus h minus f of x over h. But the truth is, when you're actually doing derivatives, you just use these theorems that help you do them, right? Like the product rule and the chain rule and so on. Similarly here, for the Laplace transform, when you're actually doing them, you're just going to use some theorems that are going to help you. Okay? So there are some basic Laplace transforms that you need to have memorized. Not really. You don't have to have them memorized because I'm going to give them to you on a table when you take the test. That table, by the way, is provided at the end of my notes. You can refer to that right now or later. Doesn't matter. But in any case, you can summarize a bunch of different Laplace transforms in that table. First of all, we notice that f of t equals 1 has the Laplace transform f of s equals 1 over s. We notice that f of t equals t has the Laplace transform f of s equals 1 over s squared. As it turns out, we also notice that f of t equals u of t minus a has the Laplace transform f of s equals 1 over s e to the negative as. Now, the rest of these on the table, we of course don't have time to go through an example for each of these, but I'm just going to write a few down. So t to the n, the Laplace transform is going to be n factorial divided by s to the n plus 1. E to the at for a real value t. The Laplace transform is going to be 1 over s minus a. Cosine of kt, the Laplace transform is going to be 1 over s squared, s over s squared plus k squared. Laplace transform of f of t equals sine of kt. This is going to be k over s squared plus k squared. And if you have e to the at multiplying by any function g of t, then the Laplace transform is going to be the Laplace transform of g evaluated at s minus a. Okay? So we're developing the table at the end of my lecture notes. I think I might have numbered these differently, ordered them differently in the table, but that's okay. Of course, the order in which you list the facts doesn't change that they're facts. So, it's often necessary to reverse this process of finding the Laplace transform. And well, what that is called the inverse Laplace transform. So taking the Laplace transform is going from this left-hand side to this right-hand side. Taking the inverse Laplace transform is going from the right-hand side to the left-hand side. Therefore, you already know how to do some of these, right? So, example. Let's say f of s equals 1 over s plus 1 over s minus 1. If you want to, and you want to find the inverse Laplace transform of that, okay? So if you want to find the inverse Laplace transform, first of all, the Laplace transform and its inverse are both linear, which means that you can take the inverse Laplace transform of each term individually, and that's okay, that is fine. Just like you can take the integral of each term individually, or the derivative of each term individually. So, the Laplace transform, f of t, inverse Laplace transform, is going to be the inverse Laplace transform of 1 over s plus 1 over s minus 1. And this is the notation that we use for it, by the way. It's the L to the negative 1. Okay. We can distribute this L to the negative 1 because, like I said, it's linear. So this becomes inverse Laplace transform of 1 over s plus inverse Laplace transform of 1 over s minus 1. And then we just look at our table. 1 over s, the inverse Laplace transform is 1. And then 1 over s minus 1, the inverse Laplace transform is going to be e to the 1t. And there you have it, folks. The inverse Laplace transform. Okay. Now, just like taking the derivative, going one way is easy, but going the other way, taking the antiderivative, is harder. Similarly with the Laplace transform, taking the Laplace transform is fairly easy, usually, sometimes. But taking the inverse Laplace transform can be much harder, depending on what's going on in your function. Okay? So let's just take a moment to talk about what sort of thing you might get here. It's very common for partial fraction decomposition to be necessary to taking the inverse Laplace transform. Remember, from Calculus 2, partial fraction decomposition does not require the presence of an integral. I mean, the Laplace transform is an integral, but that's not the point. You can take partial fraction decomposition even outside of the context of integrals, and that's exactly what we're going to do here. So let's take a look at example. Find the inverse Laplace transform of f of s equals 4 over s squared minus 9. So, the first thing you ought to do is look at the right side of this table here just to see if there's anything that actually matches up. The answer is there's nothing that matches up. You have s squared plus some things here, but never do you have on this table s squared minus some things in the denominator. Okay? So what we've got to do is we've got to change the form of this function right here so that it more clearly matches up with one of these things on the right-hand side. And spoiler, as I said, it's often partial fraction decomposition. So let's take 4 over s squared minus 9. We can definitely write that as 4 divided by s plus 3, s minus 3. Okay. Now, if you want to do a partial fraction decomposition on this, you can write that as a over s plus 3 plus b over s minus 3. And then you multiply both sides by s plus 3, s minus 3. You get 4 equals a times s minus 3 plus b times s plus 3. You distribute, you get 4 equals as minus 3a plus bs plus 3b. Combine like terms in powers of s, and we have a plus b times s plus 3b minus 3a. That sets up for us a system of two equations that we can solve for a and b. 0 equals a plus b, and 4 equals 3b minus 3a. I'm going to multiply the first equation by 3. When we do that, we get 0 equals 3a plus 3b. If you add that to the second equation, then what you'll get there is the 3a's will cancel out, and then you have 6b equals 4. Therefore, b equals 2/3. And in that case, a equals negative 2/3. Thus, our function right here can be written as negative 2/3, 1 over s plus 3, plus 2/3, 1 over s minus 3. Okay? So, from here, we just need to look at our table, because what we're trying to do is we're trying to take the inverse Laplace transform of negative 2/3, 1 over s plus 3, plus 2/3, 1 over s minus 3. Well, again, the inverse Laplace transform is linear, so this is equal to negative 2/3 inverse Laplace transform of 1 over s plus 3 plus 2/3 inverse Laplace transform of 1 over s minus 3. Okay? Because you can distribute this inverse Laplace transform operator among the terms, and then you can pull out the constants, just like with a regular integral. Okay? So, the only thing we have on this table that looks like 1 over s plus 3 is right here, 1 over s minus a. So in this case, a is negative 3. So the inverse Laplace transform is going to be e to the negative 3t. So this becomes negative 2/3 e to the negative 3t. Then add to that 2/3. Okay, once again, 1 over s minus 3, inverse Laplace transform is e to the positive 3t. So e to the positive 3t. And then that is our inverse Laplace transform. In other words, what I am saying is that if you take the Laplace transform of this function right here, what you'll get is 4 over s squared minus 9. After doing some math involving finding a greatest common divisor for the denominators. Okay? Why don't we do just one more example of finding the inverse Laplace transform. Because ultimately it almost always comes down to using partial fractions to, well, I guess I shouldn't speak too soon. There is one more example that we need to do before we end this lecture. So s cubed plus s. So you have this function here as the Laplace transform of some other function. We want to find out what that some other function is. So this can be written as s squared plus s plus 1 divided by s times s squared plus 1. And then you can do a partial fraction decomposition on that. This is a over s plus bs plus c over s squared plus 1. So you multiply through by s times s squared plus 1. You get here s squared plus s plus 1 equals a times s squared plus 1 plus bs plus c times s. All right. This becomes as squared plus a plus bs squared plus cs. Combine like terms and powers of s and you have a plus b times s squared plus cs plus a. That tells you a plus b equals 1, c equals 1, and a equals 1. Therefore, b is 0. Pretty easy partial fraction decomposition, right? So, this whole thing turns into 1 over s plus 0s plus 1 over s squared plus 1. So what we'd like to do is we'd like to find the inverse Laplace transform of this. So we can take the inverse Laplace transform of 1 over s plus the inverse Laplace transform of 1 over s squared plus 1. And then we look back at our table. The inverse Laplace transform of 1 over s is 1. So this is 1 plus, then we have 1 over s squared plus 1. That looks a lot like k over s squared plus k squared, where k is 1. So we should expect the inverse Laplace transform to be sine of 1t, or in other words, sine of t. And that is our inverse Laplace transform. Now, before we close this lecture, there is one more rule that is important to point out. And let's see here. I have it written somewhere. So, find the inverse Laplace transform of f of s equals e to the negative 2s divided by s squared plus 1. Okay. Well, let's see here. That you can't really do partial fractions on because it's not a rational function. And besides that, there's nothing on the table that really looks like that. So that's why we have one other rule. F of t equals u of t minus a times g of t minus a. The Laplace transform of this is e to the negative as times the Laplace transform of g. And that covers the first, well, I have 9 facts written here, but it covers the first 8 facts of the table in my appendix. Not my appendix, but the appendix of my notes. So what we have to do here is understand that we have e to the negative 2s times g of s, where g of s is 1 over s squared plus 1. Now we're going to need the inverse Laplace transform of that, certainly. So let's find that first of all. That's g of t equals 1 over s squared plus 1. The inverse Laplace transform is sine of 1t. Okay, great. Now, according to this last rule here, we have e to the negative 2s, so a is positive 2, times capital G of s, where capital G of s is 1 over s squared plus 1. According to this last rule of the table, The inverse Laplace transform is going to be u of t minus 2 times g of t minus 2. G is sine t, so this is sine of t minus 2. And that is the inverse Laplace transform. Okay. Typically, these two rules are the hardest. They require the most concentration just to make sure that you're getting everything correct. That's why I really needed to write down g of s equals this thing, and g of t equals this thing, and a equals 2. It's because I couldn't do it all in my head. Okay? In any case, that is an overview of Laplace transforms and inverse Laplace transforms. So that's all for today. I'll see you in the next one.